Hey everybody, and welcome back to by Andy doing some NES emulation. As always, my name is Andy, and we are working on creating a Python 3 NES, NES being Nintendo Entertainment System emulator, from scratch, and yeah, we're making really good progress. So what we've been working on recently is the CPU. So implementing all the instructions and the different addressing types and everything that we need to do to be able to interpret CPU instructions. And basically reading in ROMs and trying to execute them. So in particular what we've been working on is working on the NES test ROM, which is basically a collection of all the commands that run on the NES and some expected output that you can compare against. And then that way we can just use that to see whether we've correctly implemented the CPU. So there are around 150 instructions or so. There's also some unofficial ones, but we're not going to worry about them at the moment. And what they do is each instruction does a different thing, obviously, for the CPU. So it might be an add or a jump to a memory location. And at this point, we've implemented around 120. So we started off before the stream on Monday, which we did around 60 instructions there. So we kind of doubled the amount of instructions. Now I suspect that we'd probably be getting pretty close to finish them after this stream today. That is the official instructions, not the unofficial instructions, which is, I believe, all the ones that you see here. So I think that this does not include unofficial instructions. And unofficial instructions are what exists in these question mark locations. Anyway, so yeah, let's get started and figure out where we left off yesterday and all that kind of jazz. So, I believe where we left off yesterday was that, basically we were trying to do a load from a memory address, and there was nothing in that memory address. And the reason for that is that our stack is not actually being stored in memory, which it should be. So, what is our stack? So, let me open up something here. And I might just draw what the current problem is. Sorry, I'll just have to plug this in. This one can come out. Cool. Alright. So, basically, what we've got is we have a single byte in the CPU, which is called the stack pointer. And so this can have a value of anywhere from 0 to 255, so a single byte, a single uint 8. Now, what this refers to is actually your stack is just something that sits in memory, and basically anytime you add a value to it, so this might be a memory value of 1, and then this might store the number 33, or whatever, so on and so forth. So every time you move and store more values in the stack, this stack pointer goes up, and every time you take a value off the stack and so you move it back down, the stack pointer goes down. I should do these as green. Stack pointer goes up and stack pointer goes down. So what we've figured out is that in the grand scheme of things, in the actual memory, so in our RAM is 2 kilobytes big, and basically the stack actually starts at 100 and ends at 1FFF, which is in binary. So this orange thing actually just sits in here. That's terribly drawn, but you get the point. So this is the stack that it's in here. So this maps to there, and this maps to there. So at the moment we just thought it was up here, but it wasn't. It was actually down here. So we just need to move it so it actually exists in memory down here. Cool. All right. Let's do that then. So there's going to be a few ways that we can do this. The first way is going to be finding where our stack is in memory and setting it. But basically what we want to do is anything that goes to the range 100 to, to 1FFF, 1FF, we kind of just want to route that to the stack. So since the stack is a very specific thing, I'm kind of tempted to deal with this as an edge case, but potentially, well, let's just think about it, and let's see what we do. So we want to look at our RAM and see what the structure our RAM has. So basically what we're saying is our RAM starts at 0, and then it's 2 kilobytes big, so it goes all the way up to 2000, which is in hex. Now, here when we get memory, we actually want to return self.memory, and so self.memory is just a list of empty things. So kind of what we want to do is actually, when an instruction comes in saying get me the thing that's at 100, which is position 0 in the stack, we actually want it to return what is physically at that memory location. So really what we want to do is when we write to the stack, we want the stack to write to the correct position, which is starting at 100. So we want to offset it by 100. And the stack is a very specific thing. So I think we're just going to do that instead. So let's find out anything that writes to the stack. And probably the easiest way that's going to be to do that is to find anything that uses the SP_reg. So this is where we set the SP_reg, which is our stack pointer reg. So we started at FD, which is fine, because we actually want it to be a single byte still, and we want to offset it whenever we use it. So increasing and decreasing it, those are going to stay the same. And when we print out our diagnostic, that's going to stay the same. We expect it to be a single bit and to be offset, so that's fine. So it's going to be here when we actually write it. So the bit instructions are just checking. So we want to assign the SP_reg to be the XReg, so on and so forth. So the only point we really care about it is when we're either setting memory or reading memory based off the SP_reg. That's going to be a bit where we have to do something a bit different. So here we're storing the PC_reg on the stack. So this is going to set the memory. Now this SP_reg is going to be set to 0, for instance. And if it was set to 0, then we'd want it to be writing it at 100 instead. So the correct thing to do here is either going to be, instead of calling set memory for the SP_reg, is just going to be called add to stack, and probably grab from stack as well. And I think that's what we're going to do, is just create some helper functions here. And then we don't have to remember to increase the stack size. This will all happen automatically. So let's add some functions here to the CPU. They're going to help do us that. So set the stack value, which is going to be an int, and size, which is going to be a great question. Where was I? Base instructions. Size is going to be a numbers. Import helpless.numbers, which is just an enum that is byte or short. Cool. So sets a value on the stack and decrements the stack pointer. So the reason we decrement the stack pointer is when we add something to the stack value actually starts high, and then as you fill up the stack, it actually decreases. So you kind of start at the bottom and you start filling up the stack. Cool. Let's do that then. So stack value. So what do we actually want it to do? So let's go back to our base instructions and let's just copy out this. So what did this say? So store the PC_reg on the stack. So basically we'll pass in the PC_reg as the thing to be stored, and the size, so this is going to be value. The size that we're going to pass in is going to be number of bytes as size. And then this, instead of CPU itself, so let's store the PC_reg on the stack. So now instead of storing CPU.PC_reg, which is also going to be self.PC_reg, we kind of also want to do add to do this offset. So 0x100 plus the SP_reg. Size dot value. So here we pass in an enum. We should just do this as an int. Screw it. call it num bytes as well. Yeah, so we now offset by 100. We also want to just increase the stack size. These helper methods, these increase stack size, can probably just disappear now, because the only place that they're used is where we're going to be also calling write to stack. So let's get rid of them, and instead just increase stack size. Yep, by number of bytes. Cool. That kind of makes our lives a lot simpler, and then we can delete this method. We can delete this method, and now we can just set the stack value, or we can get the stack value. Now, when we read purely from memory, so if we do a load A from memory position 1FFF, it will just naturally return whatever's in the stack. And similarly, when we store something in 1FFF, our get function will now offset by 100 for us. So when we want to get something from the stack, we'll be able to figure that out, hopefully. So let's get stack value. And we probably don't need to pass in anything here apart from the number of bytes, because we already know what the stack position is. And since it's going to make the stack smaller, it's going to increment the stack pointer. So instead of setting memory, we're going to get memory. We're going to pass in a number of bytes, and we're going to pass in 0x100 plus spreg. We probably should parameterize this. I'll do that in a second. And we want to decrease the size of the stack, and we do that by doing a plus equals. Cool. So let's do this now, where so what's this? I'll just put it in here. So self.fp stack offset equals 0x100. And that'll just make it easier when we're looking at this code later to figure out why we have these random hex values in. I should probably do this as well, but whatever. Cool. Alright, so let's find out where we use these. So instead of this stuff here, we actually just want to call cpu.set stack value to be the PC reg, and the number of bytes should be a short, because the PC reg is 2 bytes long. Cool. So we set memory, and then this also increases the size of the stack, and then we want to jump to the memory location. So that simplifies this jump a bit. Very similarly here is, actually there's a thing we need to do. When we're getting the stack value, first we decrease the size of the stack, and then we store, whoa. Okay, I really should have copied this from here. Right, so first we want to decrease the size of the stack, and to decrease the size of the stack, we add the number of bytes to the spreg, and then we want to grab the stored value from the stack. So we just want to return self.getMemory of stack offset plus spreg, and the number of bytes is going to be the number of bytes. Cool. So now this should work. So this should just be replaced with cpu.getStackValue, and that's going to be pass in this. What do we need? Just the number of bytes. Yeah. And let's copy that comment and put that there, so we know why we're doing things. Cool. What's the old PC reg? Old PC reg equals the value that we get from the stack. Cool. Now, I think here... Alright, well, what happens if we run this now? Something should crash. Probably. CPU, yeah, perfect. So similarly here, our stack push, instead of doing this kind of stuff, we just want to do CPU.set stack value. The value that we want to write is data to push, and the size is going to be this. So we want to write that value to the stack, and that handles everything else for us. Down here in the stack pull, similarly, we kind of just want to do pull data equals CPU.get stack value, and the stack thing is just going to be a byte, which is cool. Alright, so let's try running that again. Right, so now memory address equals something. So when we do CPU.get memory address, it now equals 51. And I believe if I hex that, that should equal 33. So, sweet. So our thing, our, whatever you want to call it, our stack is now working correctly. We don't need this anymore. So our stack is now in the correct place in memory. Let's put it that way. Boom. PLAs are not working. Right, so what's a PLA? So this is where we go back to our classic 6502 instruction sets and we look for our PLAs and we try and figure out what the hell a PLA is. Pull accumulator from stack. Right, so previously we will have pushed the accumulator to the stack and now we're going to pull it. We have two PLAs in a row, which is interesting. Alright. So what is wrong here? Our A match. Okay. So soft.expected A is 57 and our actual A, cp.ireg, is 58. So we got an off by one error. Let's find this in our nesttest ROM, nesttest log, see what we're comparing to, and then use that to kind of inform us. PLA, no, that's not it. Where are we up to? CE43. Alright, let's find that instead. Right, so A is meant to equal 69. This is in hex. But I should just make all the values output in hex, to be honest. Just so they match up with what we kind of see. And we do that down here. So let's just do hex of areg, hex of xreg, so on so forth. And hex of yreg. Cool. So there we go. So now we should be able to compare them a bit more easily. So we're saying that our A was 6.9 previously, yep. And our A is now 3A, whereas theirs is 3.9. Yeah, so one offset. So let's look at PLA and let's figure out what is going on. So my suspicion is that it will have been set by something like an RTI or something, which is meant to push address -1, something like that, and we haven't done that. Anyway, let's check that out. So let's find our PLA first and just see that that looks like it's working correctly. PLA. Right, which is implicit addressing and pulls from the stack. So stack pull. Yep, let's look at stack pull. So we get the stack data and then we'll return whatever comes from this function. Yep, so our pulled data that we're getting is 1 off. So nothing about this looks wrong to me. So my suspicion is what has been wrong is whatever pushed the data onto this stack position, which was 7E. Yeah, so let's try and find this specific PLA. Now, depending on how many PLAs we have, probably a lot. Let's see. Yeah, okay. So we kind of want to just find the one where the pulled data equals... Shit, what was it? 58. Yeah, so let's find the one where pulled data equals 58. And then we can use that to kind of hone down on our error. So where pulled data equals 58. Cool. And so presumably if I do this, we should hit this breakpoint once and then we should error. Yep, okay. Now let's get rid of that. Wait until we're at 58. Right, so what did we get here? So if we come up here, CPU.getStackValue numbers.byte. I kind of want this memory address is none. Yeah, okay. So we've gotten the stack value, which has incremented the SPReg, and then gotten the memory. And it's 1 off. So what stored the thing in this stack value? So let's figure out what the stack value was at this point. So if we go to here, our CPU.spreg is 127, but it's just gone through something through this function which has incremented it. So it previously was 126, unless I'm wrong. So 126 is going to mean that whatever wrote 126. So let's set a breakpoint here, and let's do it when self.spreg equals, now because it's 126 equals, yeah, just when the stack reg equals 126. Then how many of these do we hit? So how many times do we write? No, we don't. Self.spreg equals 126. Huh. What if I did self.spreg here? 251. Okay, so it's pretty high. 127, 128, and then we die. Because I'm about to minus a value here. Alright, let's set it to 127. Let's see if this helps us. So what's the value that we're writing here? 105. What's hex of 105? Is this our value that we expect? 69105. So that's a value that we pull out at the other end. So 105. Pulled data is 58. So probably what we want to do is actually write somewhere where we can look at this memory, which is something we knew we were going to have to do eventually. CPU.getMemory. We kind of just want to honestly have something where we can expose the RAM. So CPU.RAM.getMemory. and this is a list, and we actually kind of just want this to go from 0x100 to 0x100 plus 0xFF, which is the maximum value that a stack can be. So these 255 values are actually our stack. And you can see that we've stored some things and we haven't stored others and whatever. Cool. So let's, now that we've got a view of our stack, let's unset this. And let's just run this again until we get to here. Now we've just pulled this data out of the stack. But unless I'm wrong, getting the stack value is not going to overwrite what's in the stack. So this thing here, CPU, so what's our CPU.spreg is 127, which means that previously, if it's 127 now, it should have been 126 before. And then it got added, and then we returned a value we returned the value at 127. Right. So that's why. Yeah, which is 58, which is the data that we're getting, and we expect that to be 57. Yeah, so we do want this. So we do want this set stack value. Oops. So we do want to do this when self.spreg equals 127. So we want to see when something has set this. And how many things set this? 127, no, 1. Okay. So what is setting this? Set stack value. It's a stack push. And it's a PHA. Right, so the PHA is probably the cause of our problems, which is push accumulator onto stack. Alright, push accumulator. So what is our CPU's accumulator at the point that we're writing this? Oops, self.cpu, self.areg. 105. Yep, and the hex of that is going to be 369. What do we expect it to be? Here we go. Yeah, so A is 69. And then we expect PLA to pull the accumulator, so to set it based on what's on the stack. But I would have thought that we're doing a PHA, which is going to be pushing the thing to the stack with a value of 69. So then when we pull it out, it should give us a value of 69, but instead we get a value of 3x. This is 105, which is self.areg. Am I going crazy here? So we're setting the memory, and we're going to set value 105 to be spreg to be at 127, and then the next time we're going to read in 127, so if we look at self dot, so this is before we write it, but so 127 shouldn't have everything written in it, but we should be about to write the value 105, and then down here when we're trying to pull it out, the pulled data that we get out is 58. So we can see that 127 does have the value of 58 in it. So we're writing 105 to it? Am I crazy here? One, 2, 8, 1, 2, 7. So probably what is happening is after we do this, right, where location equals 0x100 plus self.spreg, actually plus 127. We're probably going to write the memory manually. Right. Okay, so we did set is through the stack, like through stack operations, and now we're actually manually writing that memory location for some reason. But the stack point is not being changed. So what is doing this? Oh no. This is literally just directly after that. Alright. One, 2, 7. Alright, let's set anything on the RAM. Let's find out what's changing this. Def get memory. Yeah, okay, so set memory should do this. Get memory allocation. .105, so it's set to 105. And then when we pull it out, it's 58. Am I crazy here? So now the value that is written to this should be 105. It is 105. And then later on, when we come back to it, with this PLA, stack pool, get stack value, instead of being 105, this thing is now set to 58. That is confusing. Alright, well, I'm stumped. PLA. So PLA is setting the areg. Ah, shit. So it's this PLA is setting the areg to 39, and then this PLA is going to be setting it to CE. Whatever the hell CE is. 0x CE. It should be 206. And the value we've got in here is 206. So it's whatever is setting this is setting it to 58 when it should be setting it to 57. I'm unsure why I can't capture what is writing that. Do I have any other way of setting memory? And 58. How would I know? 39. So I mean the value I'm looking for is 39. See if that's anywhere pertinent. How do I turn this crap up and figure out where I am? Here we go. So this BCC seems to be the only place where 39 appears. Yeah, okay, so it's BCC. branch. Branch on carry clear. Okay, so that's not it. Oh. RAM bit instructions. Pull data. CPU.stack. So how many of these do we do? Not many. 1, 2, 3, 4, 5, 6, 7. That's the one that sets it. So the 6th is the one that sets it. So 1, 7, 8, 9, 10, 11. And the 11th is the one that we care about. So let's go to 11. Oops. 1, 2, 3, 4, 5, 6, 7, 8. 7, 8, 9, 10, 11. Shit. On the 10th. 6, 7, 8. 7, 8, 9, 10. So this is the one that we care about. And this is the first PLA. So the CPU, before we do this, so let's look at what's the CPU.spreg is 126. But when we get the stack value, we decrease the size of the stack first. So we are going to be reading from 127, which does indeed have a value of 58. Alright. Cool. So this is kind of working how expected. So what's the instruction? So this is the one that's going to set the memory. 1, 2, 3, 4, 5, 6. Which is a PLA. Oh no, it's not going to be the one that's setting the memory. It's just that breakpoint is hit. PHA 105. Yeah, so this memory is definitely being modified. Get memory owner.set. So we kind of want to do this function, and we want to set a breakpoint here. Anytime the position equals 0x100 plus 127. Yeah, so anytime we're writing to that position, we want to get a notification. Yep, so we're writing 105. I'm going crazy here. 127, 58. Whereas the first time I do this, one two seven is 0, and then I set it. And now it should be 105. And then I get to here, and it's 58. So it's managed to set this bit in RAM without going through this callback. So are there any instructions that would allow me to do that? So that might be what I'm missing out on. Yeah. Mention carry clear. Is there any way to... is there anyone that accesses the RAM? I mean, let's find all usages of the RAM. It's in memory owners. Get to memory owner. Okay. Position equals 0x100 plus 127. Self-dot get memory. So let's duplicate this. So let's get the memory currently as it stands, and 127 is going to be 105 the first time that we get it. And then the next time that we get it, it's going to be 105. 0x100 plus 127 is 58. So 0, 105, 105, 58. Alright, so I can't track this down, but let's just think about this. There's going to be an off by 1 error. It's pulling from the stack. So something that we're storing on the stack has an off by 1 error. And that value that we're storing on the stack is 58. Alright, so do we ever set a value of 58 on any memory? So setting, don't really care, don't really care. So we never set a value of 58. So we're definitely not going through the CPU set memory thing. Alright. Let's go through our functions then. So PHP, no. What is stack push functions going to do? They're going to set the stack value. So they're definitely going through this thing here. So there's nothing here where value where data push is going to equal 58. Nope. Alright. That's fine. So all these stack pulls can't be the ones that do it. So we do change the SP reg and stuff like that, but that shouldn't be a huge deal because it should still just work. Is my thought. Changing the Y regs, the X regs, so on and so forth. So it's not going to be a stack push. It's not going to be a stack pull because that's not going to write anything. Register modifier updates register. Yeah. Unless it's the X reg PLA. Yeah. I mean, it's got to be something that's setting a value on the stack, which I presume would only be stackable. LD nope branch set, branch clear, RTS. Yeah, okay. Let's see what jumps have, because jumps store values to the stack. We actually don't care. We just care about storing the old PC reg on the stack. Could that ever be it? Could our CPU.pcreg be written by this? Nope, 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 nope. Holy shit, we do a lot of jumps. Yeah, that wasn't it. Okay. Well, we do a lot of instructions. For real? Overflow will encountered in nearby scalars. That's probably expected, seeing as how... What's that Y value? FE. FF. 1. So Y keeps getting decremented until it flips over, which is what we expected. Yeah, okay. So I don't really care about them. Alright. The expected value on the stack is 57 and the actual value is 58. I don't understand how something is writing to the stack. 7E is where it gets it from. One, two, six. No, that's where it's... Alright, so let's do this. So if location in 0x100 plus 126 so is there anywhere that we go around there? Value 51, 105, 52, and 58. What was that 51? Was a stack push, was a PHA. Was a push A. I really have no idea. I mean, something like a load A, right? Is still going to go through something, right? Where's load A? CPU data. Oh, sorry, I want to store A. Uses writes to memory, which uses set memory. Yeah, okay. Value equals 58 or value equals 57. so that never happens. Holy shit. Alright, let's go hardcore on this. So every time we execute an instruction, cpu.ram.check. So RAM is of type RAM, def check. Return self.memory 0x100 plus 127. We want to print this. $58, 105. Here we go. So zeros up until it's 105s, and then around here it changes to 58. TXS and then JSR absolute. So we do this after we have executed the instruction. So after we've executed TXS, it's 105, and it's after we've executed JSR absolute. Yeah, okay, JSR absolute. Do we have any other of them? We do, okay. Nintendo sucks. Fair enough. JK. Yeah, look, I wouldn't say Nintendo's all that great nowadays, but definitely at the time they made some cool consoles. This one being one, hopefully. Right, so let's put an instruction, a thing in here, where for the CPU, self.pcreg equals that. And the instruction should equal, sorry. Let's breakpoint. Self.instruction should be a jump absolute. Right, so we're at the right place now. We get the data bytes, we print some stuff, whatever. Then we compare, it should be fine. Execute. So execute is the thing that we want to jump into. So pcreg, yep, we don't really care about that. Instruction.execute, this is what we want to do. Will you do a Sega Genesis one later on? Probably not, to be honest with you. I've already bitten off probably reasonably more than I can chew. This is kind of my first emulator that I've ever done. So I'm jumping into the NES, which is kind of complicated. There was someone that was in here yesterday talking specifically about how they couldn't find any good documentation for the Sega Genesis, actually. So I suspect it'll be a lot harder than this, which I already find pretty hard. Alright, so value. Yep, and the value is going to be none, right. So let's step into this. So we are setting the stack value based on the PC reg. And the number of bytes is going to be a short. Let's step into this. Oops. So set memory, set stack value. So what's our value? 52. Yep, so what's our set memory? And what's the SP reg? 128. This looks promising. Oh my god. So we're setting 128 and then we're setting 2 bytes up. Holy shit. Okay. So this is what's happening. Oh man, that's so depressing. So we've got a memory value at 127, 126, 128. And so this memory value is set to 105. This one's set to something else, 10. What documentation do you have that will help you? Is there a tutorial? There might be, I guess, but the NES is very well documented. So the basic the reason why it's well documented is that it uses the 6502 as its CPU. So one of the big things is doing an emulator is emulating the CPU, and there's a hell of a lot of documentation on this 6502. As well as that, there's something called the NES Dev Wiki, which there may or may not be an equivalent, but for the sake of it, this is quite a nice one, which is basically just everything to do with the NES. So a reference guide for the entire architecture. So how does the CPU work versus the PPU versus, file formats, all this kind of stuff, and just help. So if you wanted to start writing something like an NES emulator, this is a really good place to start. So I use this a lot. I go into the CPU, and then I kind of follow links from there to figure out, hey, what's the startup state or what instructions, And it's being so to come back to this, it's been overwritten by something that writes at byte 1228, but writes 2 bytes. So it writes a memory address upwards, which looks something like this. So these are actually one value, which actually equals 52768 or something. But how do you make it into an emulator? That's a great question. So the basic, probably the easiest answer I can give is that I've been writing an emulator from scratch. So I kind of, at the start, I went through and did a few episodes on what this kind of stuff is and on how to understand it all and what we need to be doing. So the topic itself, you can probably find easier tutorials on how to write emulators, but if you wanted to find an idea of how to write a NES emulator, I'd recommend watching the episodes that I've done. So all my things that I record, I put them on YouTube, and you can go back and watch them, and I try to kind of explain it from first principles. All the code is written on stream as well, so everything that has been done on this is recorded and done on stream. Okay, so that's why we couldn't catch it using the value or using the memory location, because we were actually writing 2 bytes up. And anything you can link to, I can link to NES Dev Wiki. Let me just jump onto chat. So NES Dev Wiki is going to be where you want to start if you want to do something relating to the NES. For emulators in general, you'd have to search around. I can't give you a specific resource on that. So there's the NES Dev Wiki, and here is my YouTube channel where I do all the things from the start, from scratch. So yeah, if you did want to do it, you could just hit that up. Cool. Alright, so the reason that this is wrong is that we're one off is because when we're doing a jump absolute, holy shit, that took a while to figure out, but we got there in the end. So when we're doing a JSR, we actually want to push PC plus 2, PC plus 1, PCL, PCH. God, these acronyms are killing me. What the hell is PCH? No, maybe this one will have a better example. JSR. So JSR pushes address -1 of the next operation onto the stack. Okay. So we actually need to go to our JSR instruction, which is going to be jump. JSR. Does jump set the thing -1? Is there such a thing as a jump instruction? There is. No problem, Scorpion. There are more generic. Basically, there's some. Actually, one thing I can recommend. So there's a guy that watches the stream and comes along and helps called Danny Tup. And he wrote a tutorial recently on writing a chip 8 emulator. So basically, a chip 8 emulator is a super simple system. Basically, like you can see here, pretty much you might be able to implement Pong in it and stuff, but it's like a really simple console. So it's actually really easy to implement. There's a very limited amount of instructions, and he wrote a really good tutorial. It's written in C#, but it's pretty similar on how to do a really simple emulator. So I might actually link that, because that's probably the best resource that I can give. And this is very well written and well explained. So if you want to learn how to write an emulator in general, I would read this tutorial. And then if you want to learn how to write a Python NES emulator specifically, yeah, watch this series. Cool. Jump. Okay, so JSR. So JSR actually needs to push PCReg -1, and then RTS is going to be, it's going to have to pull it out and then add 1 to that. It's the next operation onto the stack before transferring program control. RTS transfers program control to that +1. So now if we do this, it shouldn't change anything, but it should mean that we keep going. Holy shit. Alright, fix the bug. Oh man. That took way too long. Alright, so writing multi-memory bytes in memory can be hard to catch. Jeez Louise. Alright. Instructions not found. Alright, let's get back to implementing instructions. I mean, we're a fair way in now. We're up to CEAB. So if I go back to the NES test log, and I find that, how far in are we? Yeah, okay, maybe a fifth or something if we're lucky. Don't even remember which one I was looking for. 40, I believe. 40 RTI. Return from interrupt. Right, okay. So we want to implement an RTI instruction. So it's going to pull these from the stack. So it's going to pull the stack register and pull the PC. So let's find RTI here. It retrieves the flags and the program counter from the stack in that order. So it first gets the word, it first gets the status and then gets the program counter. Note that unlike RTS, the return address in the stack is the actual address. Okay? So we haven't implemented RTI, have we? No. So let's implement an RTI. From stack, it's going to be an RTI, which is this a jump? Return from interrupt. Yeah, this is a jump. So it gets get the stored status from the stack, and then we want to grab the stored PC reg from the stack. Note does not is exact PC reg, not PC reg +1. Cool. And status equals CPU.get stack value, and we want to get the status, which is actually a numbers.byte. So we're going to get a byte off the stack, and then we're going to get a short. So the status is this, and then we kind of want to do CPU.status reg dot from int status, which I believe is what we want to do. Yeah, so we want to set the status reg. Alright, where am I at? Here we go. So get the stored status, and then set the status reg, and then we want to grab the stored PC reg, and then we want to jump to that location. Cool. So RTI, the only mode is implied. So let's go to jump instructions and implement that. RTI which has implicit addressing and inherits from RTI, and the identifier bytes are going to be 40. So now this instruction should work. Missing one positional requirement, so no bits to ignore. Cool. So our thing is wrong, which makes sense. So what's something that creates an interrupt flag? But something like a break. We haven't come across one of them yet. Okay. Unless we're meant to have come across a... Yeah, where's interrupt actually? So break causes an interrupt. Yeah, you must clear RTI. Okay, so break. We should... So let's find our RTI there. Let's find our break. No breaks. Okay. So we just have an RTI instruction. So it's trying to return from an interrupt when there hasn't been an interrupt. Or maybe something else has done an interrupt. Alright, let's see. So what is wrong? Our P match is wrong, which means our status is wrong, and we can kind of see here that the 1, 2, 3, 4, yep, 5, 6, the 6th bit is wrong, which is also known as the 5th bit if you're counting from 0. So 0, 1, 2, 3, 4, 5. So this one is wrong. Which is kind of this irrelevant one. No effect used by the stack copy. See note below. So this is one of those things where you have to come back to here. We'll go back to our status flag behavior. So this is kind of where the NES dev wiki is good. The B flag. Yep, this is what we need. So there are 6 and only 6 flags in the CPU register. So basically this status reg is a single register which stores random status bits about the what's going on. So did the last operation result in a 0, or was there an overflow, that kind of stuff. Status flags. Yeah, here we go. Cool. Alright, so 2 interrupts, and so basically depending on how the interrupt has happened, we want to set different bits for 4 and 5. So basically PHP versus break versus IRQ versus NMI. So 2 instructions push the flags to the stack. In the byte, bit 5 is always set to 1, yep, and bit 4 is 4 if it's from an instruction. So do we have any break instructions in our NES log? No. Do we have any PHPs? Yes. So presumably PHP is going to be the thing that has been set. Yep. This set bits 4 and 5 to be 1. Two instructions, PLP and RTI, pull a byte from the stack and set all the flags. They ignore bits 4 and 5. Right. So when I've done... Yeah, so we just need RTI to ignore bits 4 and 5. So when I've done my PLP, I've ignored bits 4 and 5. And when I do my RTI, I also just need to ignore bits 4 and 5. And now this should work. Cool. We have a working RTI. So the problem there was that you just ignore these bits 4 and 5 when you're doing an RTI, basically. Which is something we'd come across before. Alright, instruction not found, 4A. 4A, LSR. Well, let's find the LSR, logical shift right. So LSR shifts all bits right 1 position. Bit 0 is shifted. Alright, so let's just do it. Oops. So where are our base instructions? We're in our base instructions. Let's go down here somewhere and put it in. Alright, so we've got an LSR, which is just going to be from an instruction. Shifts bits right, and I'm just going to put in this description because this seems quite good. And like always, we're going to find out what it modifies, which bits in the status reg it modifies, which is the 0 and the carry bit. So it sets the 0 bit, and it's going to set the carry bit. So it's the carry bit? Right, so we're going to have to set the carry bit manually, because we don't have a sets carry bit thing. Okay. And this is probably for the best because there's some custom logic around what you set the carry bit to be. So we want to shift all bits right 1 position. 0 is shifted into bit 7. So let's do bit instructions. It's kind of an arithmetic instruction. Right, so we've come up with a structure yesterday where we can generate all the types of addressing for a particular instruction. So here we're doing LSR instructions. So what we're saying is, this is just a string that we paste in from the documentation. We say, this is the type of addressing. So for each immediate, 0 page X, so on and so forth, we want to create a different class that represents a different instruction. And it can be identified by its identifier by here. So we just parse this string using regex. So we'll just copy this from here. We parse it using regex, and we just say create 1, 2, 3, 4, 5 instructions, 1 for each different type. Cool. And then so for generated types from LSR, use the LSR class. We just want to store these. So now, when we do this, no type accumulator. So we have a new type of addressing that we've never seen before. Accumulator, which is going to be accumulator addressing, which again we've never seen. So we're going to have to make this. I don't think we've ever seen. No. Right. So we've got implicit addressing. So let's make accumulator addressing, and so the purpose of this is it's just going to get the value from the accumulator. And there's going to be no data length, presumably, so we're not going to have any data come along with it. Yep. And the data that we want to return is actually just the cpu.areg. Cool. And now in our helpers, we just need to import that. Alright, let's run that again. Accumulator. Spelling. Cool. So now we have an LSR accumulator class. So this is going to be automatically generated by this code that I was talking about. So this is based off this. It creates a class which has now been called, and we're now in this, so it inherits from this LSR and so on. And it uses the addressing as a mix-in. So the value that we want, the value in the CPU reg, A reg, is going to be 1, which we can see over here is correct. Right, so we want to shift all the bits right one position. 0 is shifted into bit 7, and the original bit 0 is shifted into the carry. So we actually just want to CPU.areg shift everything right, which is this way, by one position. So CPU.areg equals CPU.areg shifted right by one position. Now, if I do this, this returns an int 64. So we actually kind of want to make sure that we cast this the right way. So mp.uint8 of the CPU shifted is going to be 0. Right, so if I did of 0b101 here, it should be 10, which is 2. That's correct. So I just need to make sure to cast this uint8. So all registers distort a single byte, which is uint8. So unsigned thing that can go up to 255. Expected integral d type instead. Yeah, whatever. That's fine. Now our CPU.areg should equal 0, which it does. All right. So now that we've shifted all the bits to the right, 0 is shifted into bit 7, and the original bit 0 is shifted into carry. Right. So this will shift 0 into bit 7, so that's done automatically, just by doing a right shift. And the original bit 0 is shifted into the carry. So this is what we need to do. Now we've still got the original value stored in value of the CPU areg. So let's use that. So the carry bit, so CPU.statusreg.bits status.status_types.carry. So we want the carry bit to be set to the 0th bit of value, which is just going to be value and 0b1, I think. So the number 74 ended with 1 is 0, and the number 75 ended with 1 is 1. And then we just want to cast this to a bool. Done. Okay. And we want to set the 0 bit on the result of the areg. Cool. So shift the bits and then set the carry reg. Oh, yeah, whatever. Cool. So this should work, but obviously it doesn't. So what's wrong? P match. Okay, so what P doesn't match? It looks like the most significant bit, which is probably the carry bit, if I had to guess, but might not be. So the most significant bit, which is the negative bit. Alright, and we have said, where was I? Jump instructions, base instructions, go. So sets the 0 bit, but doesn't set the negative bit. That's what this is telling me. Whereas this tells me that it does set the negative bit. Because S means negative. I haven't quite figured out why S means negative. So this should probably just be a plus, and it should set the negative bit. So that's just the documentation being a bit wrong, but that's fine. Cool. So that worked. So we're on to our next instruction, which is 0A. 0A. ASL. Arithmetic shift left. Cool. So let's do this again. Here we go. So LSR, and now we're doing an ASL, which is going to be an arithmetic shift left. Shift bits left. Let's do the same thing where we copy this description because it's quite nice. And we know it's going to set the negative, the 0, and we're going to have to set the carry manually. Right, so we want to shift bits left one position. By casting it into a U8, we ensure that it'll never go over our... Oh no, because this will overflow. Holy shit. So 0 is shifted into bit 0. Yep, which happens automatically when you do a shift left. And the original bit 7 is shifted into the carry. So what we kind of want to do is take the original bit 7 out. So original bit 7 equals value or whatever, cpu.areg ANDed with 0b10. Yep, so this will get the 7th bit out of here. Let's just quickly implement all the different types of instructions. So ASL types, I'm just going to use the ASL class, and then we just need to copy this in. I don't know why these have caps and other things don't. Cool. Whatever. Just make sure that works. Alright, yeah, that should work. So let's try and set a breakpoint in here and just ensure that we are getting the original bit 7 correctly. Okay, we can't do lower then. Yeah, okay. It's a bit weird. Arithmetic instructions, so let's come back to here and let's change all of these. What the hell is that? Okay. I don't know why these are written in a different format. Anyway, accumulator 0 page X, absolute and absolute X. So it's actually the same as LSR. Except these should be... Yeah, okay, don't do that. Basically I want to copy this, and I want to put this here. Nice, multi-line select. Alright. Invalid literal. Oh, and they have these weird things. I'm not so sure why the format is different. Am I reading the wrong page? Oh, I totally am. ASL, okay. I meant to take them from here. Cool, so the original bit 7 is 128, and we actually just want to shift this by 7 probably. Let's just make sure our order of operations is correct. So this is going to be 1, whereas if we did 127, it should probably be 0. Yes, that's the original bit 7, and then we want to shift everything by 1, and really what we want to do is areg without 7. So it's cpu.areg, and we kind of want to do a bitwise and with 0b 111111. So with this, but except this be a 0 and everything else be a 1. 1, 2, 3, 4, 5, 6, 7. So this should probably equal 0. Yeah. And if we did 1, 2, 7, and with this, it should equal, whoa, 1, 2, 7. Cool. Yep, so we take the bit 7 out, and then we shift it. So we shift all the bits one position, but we've taken out the 7th bit, which is shifted into the carry. And we'll just do the bool of the original bit 7. Yeah. And 0 shifted into bit 0. So that should just be what we need to do. Yep, so we take the value, then we set the areg, then we're going to find the bit 7, and then go from there. Right, cool. So that's some bit shifting done. ASL doesn't work, hardly surprising. Why doesn't it work? P doesn't match. Why doesn't P doesn't match? Because the carry bit is set incorrectly. Alright. So maybe this is wrong. So what's our original bit 7? 128. It should just be 1, right? Original bit 7. Did I do something wrong? Value. Value ended with that. Ah, brackets. Always use brackets. Original bit 7 now equals 1. Alright, so that's just an order of operations error. Instruction not found, 6A. Ooh la la. Alright, 6A. Roar, which is rotate, I think. Rotate right. Okay. Let's look up raw here as well. So, cool. Let's keep doing what we're doing. So we're going to do a raw, and then we'll do a roll. But it shifts bits right. But instead of being arithmetic, it's going to rotate them. So it's going to shift bit 7 to bit 1, or bit 7 to bit 0, or the other way around. So the carry is shifted into bit 7, the original 0 bit is shifted into the carry, right. I'm going to assume that it does the same kind of things, SVZ, yep. So we'll need to set the carry bit as before. Right, so it shifts all bits right one position. So we're going to copy this shift right code. Shifts bits. So the areg is going to be shifted right. The carry is shifted into bit 7. And the original bit 0 is shifted into the carry. Right, so let's set the carry, let's get the carry flag to set. So get the bit to set the carry flag. Oh, we can just do this off value. So I want to shift the bits, and then we want to shifted bits without 7, and then we want to add 7. So we've shifted all these bits to the right, and then we want to add bit 7. And how do we add bit 7? Shift carry shifted into bit 7. Shift bits without 7. Can we just binary OR it? if it's a 1, yeah, but we'll need to shift it. So shifted carry equals the int of this shifted that way 7 times, and then CPU.areg is just going to equal shifted bits with 7 ANDed with the shifted carry. Now, yeah, whatever. np.uint 8. Okay. np.uint 8. Cool. Yep. Cool. So let's do the same thing where we implement these types, and then we'll come back and, you know, debug it. So raw types is a raw. Let's import that from raw types. Let's head back here. Let's find our raw. Done. And now we should be able to head down to here, and we should be able to breakpoint. Cool. So what's our shifted bits with that 7? More importantly, what's our value? Our value is 1. So our shifted bits without bit 7 should be 0. And our shifted carry should be 128, or it should be 0. So it's either should be 0 shifted by 7 or 1 shifted by 7, which is 128. Yep, that seems right to me. And then this shifted with this should just be 0. Wow. So I think we need a bitwise OR. Should be 128. And what if I did like 12 here? Should be 140. Yeah, that works. Okay, so bitwise OR that. Shift bits. So we've done the areg now, and the carry has been shifted into bit 7, and now we just want the original bit 0 to be shifted into the carry. So I want to set the carry reg to be the bool of the original bit 0. So being a value is that, yeah, so the original bit 0 is just going to be ANDed with B1. Yeah. So I think that's right. So to set bit 0, to set this based on bit 0, we just need to AND it with the value of 1. So that'll either equal 0 or 1. Cool. Yeah, that worked. While we're here, we may as well implement ROL, because I know that exists. Shift bits left, and is right here. So let's do that again. So shift bits. So the carry is shifted into bit 0. Okay, so shifted bits without 0. And we're going to shift left, so we're going to shift up. Do we actually want this? So when we're shifting up, we've just got to be careful about not overflowing. So shifted bits without 7, yeah, that's fine, because we're shifting down. But when we're shifting up, we've got to be careful. So I'm going to leave this as this. So we're not going to cast it to a uint yet. Shifted bits without 0. and the original bit 7 is shifted into the carry. Yeah, so we've got to worry about not overflowing here. So we've actually got to take out the 7th bit. So to do that, so value without bit 7 is just going to equal cpu.areg ANDed, no, ORed with, no, ANDed with 0b, 0, 1, 2, 3, 1, 2, 3, 4. Right, so if we AND it with that, then it'll make sure that it turns off this high bit. This is the value without 7. And then this is the thing we actually want to shift. Shift the bits, and now it doesn't have a 0. Yep. The carry is shifted into bit 0. So the shifted carry, we don't need to shift at all. We just need to have it be a 0 or 1. And then the areg result is just going to be shifted bits without 0. And that is going to be ORed with the shifted carry. Yeah, which is going to be 0 or 1 in the lowest bit. Yeah. Okay. And then we want to set the carry reg, the original, to be the original bit 7. I feel like I've done this before. The original bit 7 is shifted into carry. I have. So the original bit 7 is going to be value. We're going to get the highest value, shift it, and then set it. So I think this should work. Let's try that out. So RL instructions. Let's copy our ROL types, which is going to be these. Let's give that a go. So, and perhaps, oh no, it did work. Wait, do we have an ROL? Hell yeah. Alright, our ROL's worked. That's pretty cool. It's not usually, I don't usually get bit shifting right the first time. Yeah, cool. So that's important to do so we don't overflow, which is kind of good, a good thing to do. It probably wouldn't matter because this shifted bits was 0. Oh no, it would matter. Yeah, anyway. That's smart. Yeah, we do that with that here. We do areg without 7. I'm going to copy that across then. Right, okay. So what's wrong here? What's the instruction we're looking at? An LDA indirect X. A match is wrong. P match is right. Okay, so it's just our A is wrong. And we can see that our areg equals 4, and our expected A is 93. Right, okay. Load A indirect X. Let's see. Areg is 4. Right, and we expect it to be 93. So let's look at our LDA code. Not sure why exactly this would be wrong, but let's do this when value equals 4. So do we have many of them? 3, 4, 5, 4. Okay. 1, 2, 3, 4. Wait. 1, 2, 3, 4. Okay, 1, 2, 3. 1, 2, 3. Cool. So LDA indirect X. CPU areg equals the value. So how did we get this value? What is the memory address? Is 0. And I guess if we looked at our self.cpu.ram.getMemory, it's just CPU. The value at 0 is indeed 4. So my suspicion is that what is the value that we want to see? We want to see the value 93. Is that anywhere in our memory? So let's just do a bit of a list comprehension on this. So x for x in this, if x equals 4, and that should return a single value. Yep. And does anywhere in memory equal 93? It does. We kind of want to know enumerate I. Kind of want to write the index 1024. So now if I do cpu.ram.getMemory 1024, it should return the value of 93. So the fact that we expect it to, the value where it found it is 1024, and instead we're getting 0, indicates to me that we're off by a factor of 2 to the 10. Seems like we're getting a wraparound error or a wrapping error or something like that, which does not surprise me. Alright, so let's look at that then. So it uses indirect addressing. So let's open up our addressing, and clearly we've got some kind of problem here. Now which indirect addressing does it use? Indirect X. Indirect addressing with X. Zero page addressing with X. So adds X reg offset to absolute memory address in the first 256 bytes. Right. So this is 0 page with X, and then we go to that value and we find something. So what is... Okay. So let's think about this. LSB location. So we kind of want to find... Yeah, we just want to find when this is this. So let's go back to the CPU. And let's set here when self.pcreg equals this. We'll get rid of this. Cool, so let's step through now. So execute memory address. We do care about this. So we want the LSB to be something. What's the LSB location? 255. Okay. What's the xreg? CPU.xreg is 0. Yep. So we get a byte in the first 255 bytes, which is 0. You know, that's perhaps what we expect. A1FF, yep, so we want to find the thing that's at FF, and then we want to look at 255 and 256, LSB, MSB, whatever. So what's the memory location that we end up wanting to look at? 0. Right, so what's our LSB and what's our MSB? They're both 0. And what this is saying is CPU.ram.getMemory, 255 and 256 both have values of 0 stored in them, hypothetically. 255 and 256 both have values of 0. Yep, that's true. And what do we expect them to have? We expect them to have values of something different. So we can tell that 255 has actually been set, which is cool. And if we expect the LSB to be that and the MSB to be this, what do we want to equal? 1024. So what's 1024 in hex? Is 400. So we would expect the value at 256. Here's an interesting thought. We would expect the value at 256 to be 4. The value at 0 is actually 4, which indicates to me that it's actually, this function is working fine. It's whenever we wrote 4 to 0, that was wrong. That was meant to be written to 256. We've wrapped when we weren't meant to wrap. So let's do when location equals 0 and value equals 4. Do we hit that? We hit it once, yeah. Okay, so what has done this? So writes to mem has done this. Update a value. STA 0 page. And the memory address that we expect is 0. So the data length. Yeah, so what are our data bytes? This data byte's 0. It's probably just going to be 0. So we're saying write at 0, but somehow that's meant to end up at 256. Let's look at store A. See if it gives us any hints about why this might be wrong. Holy shit. Nope. Store A. Nope. So 0 page gives us a byte in the first 256. I can't expect that it would want us to wrap around like that. Ah, shit. Okay, never mind. So instead of byte 256, alright, no, that's right. So it turns out when we're doing addressing, when we're doing LSB and MSB, these should actually just be mp.uint 8. We expect this to wrap around back to 0 instead of being 256. That should work now. Alright, value is none. So or A indirect X. Yeah, okay. And what are we saying our memory address is? Is 512. And the value is none. Why is the value none? When are the other times we hit this OR? Immediate, immediate. Right. So this should be going and retrieving 512. And so OR as well as AND. How many ANDs do I have? And they all immediates? These actually need to read from memory. These don't writes to mem, but these reads from mem, I believe. So OR should reads from mem. Is that going to fix my problem? Yeah. And should read from memory. EOR should probably reads from memory. Should ADC read from memory? Well, let's see. ADC should read from memory. Pretty much everything should read from memory, really. SBC should therefore read from memory. LSR probably doesn't need to read from memory, does it? Oh, no, this comes from ADC. Sorry. Cool, alright. How far in are we? D, we're up to D. We're making it. Slowly and steadily. Alright, overflow, yeah, whatever. What's the problem here? P-match, false, story of my life. The carry bit is not set correctly. Alright. What instruction are we on? The compare indirect X or JSR absolute? Let's find out. Instruction results not expected on the JSR. Okay. So JSR, oops, base instructions, JSR. Let's look at JSR here, see what it says. JSR pushes address -1, yep, onto the stack for transferring program control to the following address. Jump to subroutines, okay. Nothing really. It says push PC +2, yeah, whatever. PC +1, PC. Yeah, okay. What is it? Is that actually the carry bit? That is the carry bit. 1 if the last addition resulted in a carry, or if the last subtraction resulted in no borrow. And we expect it to be 0, and for some reason it is set. That seems around right. That's wrong. Don't know why that would be right. Ooh, yeah. So expect it to be could it be this compare? right, it's probably this compare. So what the hell is value? CPU.areg. This one, breakpoint if CPU.areg minus value is less than 0. Oops, so how many in do we get? 1, 2, 3. 1, 2, and on the third it goes, yep. 1, 2. So value is 86. So CPU.areg minus value is -1. Return CPU.write. So what does compare? I think we probably want this. To do that. What if we did that? So result equals that. Instead of equal -1, it should equal 255. So it's a negative bit. Okay, maybe we don't want to do this, but when it equals -1, so we're saying is 1, 2, go into that. What does this equal? This is false, and we expect it to be false. We're saying it actually is true. So this is not the compare where we're at. Alright, let's do the classic. Hit ourselves until it works. Alright. self.pcreg equals this. So the instruction what? Cool, so the instruction is a compare. Yes, it's not the JSR, it's the compare that's gone wrong. Yep, so get the instruction length, execute, get the memory address. Sure. What's the memory address? 512, sure. Get the value, 65. Write, I want to step into. Result. Result is 255. And why is that? because we are actually overflowing here when we really don't want to be. So this should be -1. Alright, let's do that. And now this should work. You know, hypothetically. Yep, alright, we got further. Unsupported type of ands for none and int. Alright. So value is none. We're on an LSR0 page. So the value that we got is 0, the memory address is 120. So what is the reason for this? The reason is going to be, we need a reads from mem. So most of these do read from memory. It makes me kind of question whether I need to do this reads from mem class. So the reason that I've done this is that some don't read from memory. This would just happen if memory address is not none. Because memory address can be none, right? So I'm just going to get rid of this. I'm just going to do this. Writes to mem has a very specific meaning. So if memory address is not none, return that, otherwise return none. Control F reads from memory. Let's just do a find and replace. Replace in path. Reads from mem, replace with nothing. Replace, replace, replace. Cool. So LSR 0 power still got the same problem. Cool. LSR 0 page is probably the one that's breaking. And what's the reason that that is because our A matches are not true. So we expect the average to be 0, we expect it to be 1, and it's 0. And we've done an LSR. Or is this the LDA's fault? I think this is the LSR's fault. Yeah, LSR. Okay, so let's go back to base things. Let's hit up our LSR. Let's see what's wrong with this. I think it's, what's this? Value is none. Alright, how many of these do we have? One, two, three, four. So if I do 1, 2, 3. Nope. 1, 2, 3. Okay, so 1, 2. So our CPU.areg is 0 and we expect it to be 1. So why is that? So let's put this up here before we do this function. 1, 2. CPU.areg is 1. Shifts bits right. LSI shifts all bits right one position. 0 is shifted into bit 7. So bit 0 should go into bit 7. Oh no, 0 is shifted into bit 7. And the original bit 0 is shifted into carry. So this should be shifted into carry. And the output should be 0. When in fact we expect it to be 1. Oh, wait a minute. What the hell is LSR's 0 page meant to do? It's actually not meant to. Is it meant to not shift the average? It's actually shift the thing in the memory. Ah, right. Okay. So I fucked that up. Right, okay. So we kind of want the areg. No, we don't want to set the areg. We want to set either memory or areg. Memory or accumulator. ASL, LSR, ROL. Alright, so all of these need to be able to either affect memory or accumulator. Okay. So when we get to our first LSR, it's an accumulator, and now it's a 0 page. Fuck. Alright. So memory address is 120. What is it when it equals none? Okay. Let's just be dodgy here. So let's do a base shift class. And it's going to shift bits. It's going to do that. It's going to have these two attributes set. And it's going to do some crap. Alright, so we actually want this to shift bits. So if memory address is none, we want this to do CPU.areg equals the value, update a value, else CPU dot set memory of the updated value. Set memory location value number of bytes. Location memory address value update a value number of bytes probably 1. Well, we know it's going to be 1, so numbers dot numbers dot byte. Cool. So what's updated value is, so this is a base thing. We actually just want to call this on value, and we want our super things to inherit and to change what needs to be changed. Right, so return value. Now the shifting and stuff we will leave up to the people that do it. Right, so what we actually want to do here is shifting the bits is we want to say updated value equals this. We want to call our super function with the updated value. CP memory address updated value. Let's cut that crap. Yep. That can go, and then we want to set the carrier edge We actually just want to return that. And then we want to set the carry reg based off value of the original thing. Yeah, okay. So that should work for LSR. ASL, let's try that as well. So updated value. We want to return this. And the bit set to original bit 7, yep, sure. ROR, same thing. So the updated value, and then we kind of want to just return that. Yep, and last but not least, updated value. Cool, so now it should set the correct thing, whether it either sets the memory or sets the areg. LSR accumulator, not working. It's perhaps unexpected that we got this wrong somehow. So cpu.areg, right, because these don't inherit from shift. Alright, we're getting a lot further. Unknown number size. What the fuck? Numbers.byte.value. Holy shit, instruction not found. We're back, alright. E6, was it? E6. Ink. Alright. Didn't we have an increment? Am I crazy here? Bit instructions in. In Y. Here we go. In X. Okay, but apparently we didn't do increment memory by 1. Alright. Well, let's do it. Increment memory by 1. And we want it to have this. So it sets the negative and sets the 0. So it sets negative bit is true. And increment. So we want to increment memory by 1. Okay, so CPU dot so get the memory and then CPU dot set memory. Original value plus 1. Now let's make sure that we cast this to something like that. Actually, this cast shouldn't be necessary. Yep. And then we'll just need to embed instructions down here. Increment. Okay, and then we should open up like load instructions and we'll copy from here. So ink types. We want type ink. What are our increment types? This. Done. Increment 0 page is not working because the p match doesn't match. And this looks like several things are wrong. The second one is wrong, so probably both of them. Both the, where's my status at? So 0 and overflow are probably both wrong. So memory plus 1 stored in memory. And I'm willing to bet that I forgot to do a return here. Updated value. Actually, does CPU.setMemory return anything? No. You probably should return the value, but anyway. Updated value. Equals original value plus uint 8 1. Sure. Alright, it should work now. Wait, what? Oh, that's weird. Instruction not found, C6. Okay. Dec. One presumes decrement. Cool, there's the memory types, same thing, alright. So let's get our deck types. Let's make sure we put them in there. In base instructions, we'll just need to define decrement. It's going to be almost identical, except this is going to be a minus. Yep. And in bit instructions, we just need to import deck, and then this should work. Holy shit, we're up to... got a lot on the way in. Because we're jumping around, actually, who knows how close we are to the end, but it's a lot of instructions. Cannot find the memory owner. Alright. So what's the memory address that we're trying to access? 65587. Interesting. np.uint 16 of 65587. Yep. Alright, so we meant to have overlap here. So let's make this a PC reg. So mp.uint starts at 0. mp.uint 16. And then let's find PC reg anywhere we use it. Cool, so current address equals that. Return this plus this int.from bytes. So yeah, I just need to make sure that anytime I use this mp.uint16, let's make sure I'm casting to mp.uint16. I could just make them both mp.uint16s. I might do that. Because an mp.uint16 plus an mp.uint16 should always equal an mp.uint16. 6500. 65,000. Yep. Plus this, 6500. Yeah, it does overwrite. Cool. Alright, let's keep going then. Find PC reg equals none. PC reg equals uint16. PC reg equals mp.uint16. Let's just copy that. Yep. So self.getMemory owner of the PC reg, yep. pcreg.mp.uint16. I just copied that. I don't know why I would do that. uint16 of the data length. Expected PC reg, yeah, sure. And in instructions, PC reg equals, make sure that the memory address is 16, set the stack value, can't hurt, alt PC reg equals that. Yeah, cool. Alright. Let's give that a shot. Exception, cannot find memory owner. Ah, you bastards. Alright. Where's this coming from? Location. Where's location coming from? Memory address. Indirect Y. Right, so our PC is now in 16. Now we need to make all our addressing uint16. Fuck it. We know that's fine. We know that's fine. I mean, we probably know that's fine. 0 page is going to be fine. Relative addressing. Yeah, that's fine. Return that. And then just make sure here that we return that. Potentially that might overflow. Alright. Instruction not found. 0, 0. 0, 0. Break. Oh shit. I thought we didn't have a break. Wait a minute. Jump indirect. Who knows where it jumps to? I swear there wasn't a BRK. Break. Instruction not found. What's my memory address? What's my self.pc reg? 65280. What's the hex of that? FF00. FF00 doesn't exist. Holy moly. Ah, who knows. Okay. Let's find our break. BRK calls the non-maskable interrupt and increments the program counter by 1. Therefore, RTI will go to the address of break plus 2. So the break may be used to replace a 2-byte instruction for debugging, and a subsequent RTI will be correct. Well, that means something. I'm not quite sure what. Interrupt, push PC plus 2, push status register. Two flags. So BRK pushes 1, 1. Two instructions, PLP and PR, pull by ignore bits 5 and 4. The only way is to read the flags. BRK, BRK. Do. I is set to 1. Interrupt. Inhibit. I is set to 1. Is that this interrupt flag, or is this the interrupt inhibit? Huh. Well, this doesn't say anything, so... Oh no, set I to 1. Literally set I to 1. Okay. So let's make a break class. Where's my RTI? It seems useful. So break gets just an instruction, maybe? It might jump as well. And what is break gonna do? It's gonna set I to 1. It's gonna push this stuff. So let's just copy this, because it's gonna be the opposite of RTI. So we want to push, store the PC reg onto the stack. Note is exact PC reg, not PC reg plus 1. I don't think that's true anymore, but set stack value. And this is probably going to have to take in a value, which is going to be cpu.pcreg. Now, RTI. Grab the exact. So what has previously stored this? Self.pcreg plus 1. RTI, our break, RTS, jump. Yeah, but what stores it? So it sets a stack value. Ah, shit. So JSR sets it to -1. unlike RTS. Right, the return address on the stack is the actual address. Okay. And then BRK increments the program counter by 1. Therefore, an RTI will go to BRK plus 2. Is exact. Okay. Increments the program counter by 1. Sure. So store the PC reg, but first break push PC plus 2. So I think cpu.pcreg plus equals mp.uint 16 of 1. Increment the PC reg, store the PC reg onto the stack. Get the stored status from the stack, and then, so we don't need to jump or anything. Get the stored status from the stack. Now this is the old thing that we did. So we want to store the status on the stack. So status equals that. cpu.statusreg.toInt, I believe. Then we actually just want to store that on the stack. So cpu.setStackValue status. Yep. And then we want to just lastly do cpu.statusreg.bits interrupt status.status_types.interrupt equals true. Now there's probably a question here of whether whether this should happen first or last, but we'll pretty quickly figure this out. So BRK doesn't exist. Right, okay. Sure. Probably because it skips the PC, adds PC plus 1. So what, okay, when I write the BRK, what is the PC reg? Oh no, because now I'm up to a PC reg. Because I haven't implemented break. Now is there only one break? Break implied, okay. So I'm going to put this in jump instructions because it probably belongs somewhere here. RTI class break implicit, which is the implicit addressing and a break. And the identifier byte is just 00. Yeah, okay, and now it doesn't know what to do. So where is this? So 7B. Then I have a break. And then it goes on to DB7E. Could have been my jump is wrong. Maybe I'm not meant to be hitting a break. So let's go back here to when I equal this. So self.pcreg is equal to that. So self.instruction.execute, and I'm going to jump into destruction, the memory address. So what's this memory address? In hex. Holy shit, oops. $0xFF00, and what the log is telling me is that actually I shouldn't be jumping to FF00. I should be jumping to DB7E. Alright, what's DB7E? $56,190, whereas I'm going to $65,280. Alright. So let's go down and let's go in here again. Memory address we want to step into. So we really want to be looking at 0200. Yeah, which we're not. So at 0200. And our LSB is actually 0 when it really should be something different. Data bytes. What are our data bytes? 00. Okay, so let's go back here. Sorry. Let's step into that function. Step in. So we're using absolute addressing. C. Let's check that 6C is what we expect it to be. Is the jump indirect? Right, so it looks like I've fucked this up. Why is it telling me it's a jump? Oh, it is a jump indirect. Okay, okay. So, jump indirect will use absolute addressing. So what's this? Data bytes. Data bytes 0. So really what it should be getting me is 0x200, which should return, the value there should be D7E, but jump. Yeah. 0200, that makes way more sense. 512, yep, so that's working as expected. And class.getCPU offset is going to be nothing. Right. So super. Oh wait. Oh shit. So indirect base. Look up the bytes at there. So this address is actually going to be a uint 16. Not a uint 8. That's why. Alright, well, fix that. A match is wrong. Expected A reg. Am I at the same thing here? LDA indirect X. I probably just screwed something up with this. Because, let's look at this. What does this return now? LSB location 128, 129. 30, 30, 255, 256. Broken. So we actually do want it to be 8. Ah, shit. Do we only want this to be indirect base? So we get 255. We want this. Man, why do we want this to wrap around to 0? Why would that be bad that this is 255 and 256? We're doing an indirect. There's more than 255 values that it could be. There are many. Because we're doing memory locations. Okay. So now they're both equals 0, whereas CPU.getMemory 0 will return what we want, which is 4. Right, okay, so maybe it is what's writing this 0, which is wrong. What's writing 4 to 0? Set memory. Location equals 0 and value equals 4. One thing that does that. Yep. So what's that thing that does that? Set memory, right. STA 0 page. Ah, fuck. So when it's a 0 page, so 0 page addressing should be mp.uint8. So now it will still write at 0, and we expect it to because store a 0 page. Alright, so can store a 0 page overwrap? Let's look at 0 page. Skildrick. No. Easy 6502 by Skildrick. So maybe the 0 page can only reference the thing in the first 256 bytes, but you can go over that by adding. If the result of the addition is larger than a single byte, the address wraps around. Yeah, okay. If the result of the addition. So this should store at 0. Yeah, it comes from here, where the memory address is 0, and the reason the memory address is 0 is that the data bytes are 0. No? Data bytes. Store a 0 page. Right, the data bytes are actually 0. Okay, so it's actually intending to write at 0. Hmm. 0 page. Okay, so we store it at 0. And then LDA indirect X. Look up the bytes at this indirect. Alright, let's look up indirect then. You take the 0 page address, you add the X registers, and you look that to look it up. LSB. Oh, because each... Shit. These do have to be 8, because they each are individually single bytes. But then we... Oh no. Hold up. LSB location is 255. MSB location is 256. We actually want these LSB. So whatever comes out of these 0, 0 are going to be UN8s. And then when we combine them, we make int from bytes. And then we want this final thing to be within our address space, which is UN16. No, it should definitely be 16s. So the value that we store at 0 is definitely meant to be 0, that value of 4. So when we get here, oops, 1, 2, 3. When we get here, what does our CPU.ram.memory look like? 4. But what happens at 255 and 256? Whole lot of nothing. That's worrying. That's what I'll say. How many instructions do we have? That's maybe even more important. Started at 120 and we're up to 151. So we've made a bit of progress there. I think we're getting pretty close to the end of the instructions that are valid. So what's going on here? We expect our A. Yeah, okay, so it's LDA indirect X. Expected A to be 93. Which is at 0x400. Yeah, so the only way that this works, and we get that value of 93, is if this returns 0x400. The only way that happens is if MSB, if this is 0, which is fine, so 255 is 0, and 256 is 4. This is 4. And the only way that happens is if this get memory points to 0. The only way that happens is this MSB location is a uint 8. But I don't know why. And if I do that, that's going to break something later on. Because now when we do a jump, right, we expect to get something else entirely different. And we don't, because we map to FF00 because we're just overflowing shitload. Right. So is there any reason that this would be different for a different type of thing? I mean, I suppose when we're doing like a 0 page, it's like 0 page should overwrap. Maybe that's it. So indirect shouldn't overwrap, but 0 page should. mp.uint 16. Let's try that. Numtype. Class.numtype. So by default, let's make it uint 16. And then when we're doing this kind of stuff, we'll make it uint 8. Let's see whether that will do it for us. Nope. So let's go back to here, to this jump. Set here, which is self.cpu-reg, self.pc-reg. Alright, let's start stepping through this shit. So what's the LSB thing that we get? The LSB location we get is 767. And therefore the next thing is going to be 768. LSB, MSB. So this is meant to be looking at jump indicative 6C FF02. So it's meant to indirect, it's meant to look at the memory address 02FF. 02FF. Which alright. let's go back. I'm confused. In we go, in we go. So indirect base uses absolute addressing. Okay. Right, uses absolute addressing, yep. So where am I? I'm up here, which is going to be int from bytes 02ff. And somehow this equals 767. Which should be 0x02ff. Should be 767, which it is. Right, so that's expected so far. So next, so we expect 767, then we obviously expect MSB to be 768 then. And then we want to get whatever's at 767 and 768. Da, da, 0, 169 is what we expect. What's hex of 169? So we expect A900, 0xA900, which is 43,264. Now, is that what we get? Yes, it is. So this should return A900, which is 43,000. Return. So memory address should be that, yep. Value should be whatever we get from that, which is 00. So CPU dot get memory 0xA900. Updated value. Ah, shit. That was the one that I wanted to step into. Oh, let's keep going. Step. Boom, boom. Step. Jump to that memory address, which is A900. Yep. And then return, yada yada. Update, identify, compare, exception. Exception is in everything because we've jumped to the wrong address. Right, so this break is definitely not right. So let's jump indicative, whatever it is. So we jump here. Really, we want to, right. So this is saying 02ff, and the value here should be 0300. And what we found was that it didn't equal that. It equaled at 02ff. Far out. Buttons. Alright. The value at get address should be 02ff. Yep, 767. So we're saying the value, he's saying the value at this thing is 03 and 0. And I'm saying that it's 0 and 169, which in hex is A9, and he's saying it should be 03. Okay, so that's where the problem is. So, what the fuck? Alright. So, the memory that we're looking at, we know, which is 767, is 0x2ff. Alright, so let's set something on here on our memory, which is location equals 0x2ff. So let's see what sets this memory. One thing sets it, and then we're done. Okay, so one thing sets it. So this thing should be setting it to 03, to 3, and instead of setting it to A9, value 0. Who is the memory owner? The RAM. So self.ram.memory 2ff is 0. And then after this line, whatever, still equals 0. Alright, so let's go back to here and do my classic print cpu.ram.memory 0x2ff. Always been 0. So we're probably looking for 2xf plus 1. It's probably $137. Hex of 137. Hex. Should probably be A9. 89. I have no idea what the hell's going on. Get rid of that. 169. Okay. So there's that value again. So the value in plus 1 is the one that we care about. So let's do that. So let's set the thing back on here. Location equals 0x2ff plus 1. $0x3, which is the same as saying 0x300, right? Is that relevant at all? Memory map. It's not, right? 0x. You go all the way up to 800. And this is only at 300. So it's not relevant. Alright, so does this get set at any other time? Yep. 239, 112, 137, close one, 169, I believe that's our value. Correct, so who sets it to 169? Writes to mem does. STA absolute. And data bytes is 0x300, 768. And the value is 169. So why is the value 169? And that's because the CPU.areg is 169. Okay. So potentially it should be this. This 169 should probably be a 3, right? Now we've just done a load A immediate, which was A9, A9. Yeah. Which does indicate to me that we have just literally stored the value of A9 in A, and then we are storing it in 300. Yeah, so that seems right. And then when we come down here, the memory address that we get is 300, and the value therefore is oops. So this is fine. So it's meant to be A9. PC reg, go in, memory address, value. Jump to the memory address, right, so it's stored in the hex memory address, which is A9, which we think is wrong. It should be 300. So we're doing this wrong. Jump. It looks up this memory location. And the thing that's stored at that memory location is 300. Is that what I've done? Am I meant to look up? So I've got 0f. Okay. This is, I think, where we're going wrong. So I've got this command. In we go. So memory address, so this should be return 2FF and 3. And it's saying that whatever's stored there should be 300. Which is actually the hex, which is actually our MSB location. Holy shit, okay. And then we look up the LSB and the MSB, what's actually in their memory things. And the MSB, so the thing that's actually at 300, memory location 0x300, is the value 0xA9. But we actually want to jump to 300. Now why would we do that? Why would we possibly do that? Instead we're jumping to A9. 300. Alright, let's look up 6C. Let's just check that we're doing the right thing here. I feel like we've already checked this. Indirect. We have indeed done this. So, alright, theoretically, so what is LSB location equal, and what is MSB location equal? What if this was an mp.uint8? And then if this was a uint8, then it would be 255 and 0. So what's the thing of 255? Should be 0. 255 and 0. Ooh, okay. So what if we did that? DB7B. Right, so this is a different one. Go in. Go in, go in. So what's the LSB location? Jump indirect. Mm-hmm. 0, 1. No, okay, so we don't want to do that. Alright, let's go back here, let's set this breakpoint again, let's see what's going on. Look up the bytes for original address and original address plus 1. CPU.get memory, yep. Okay. So the MSB location, the thing that's stored at that MSB location is definitely 169. Do we have any other 6Cs that we can look at? Zero 200. So let's see if we go in DB7B. Does this check out? Let's go in. So LSB is 512, 513. 126, 219. What does this equal? Hex of this, db7e. So kind of what I'm trying to figure out is db7e. Yes, this does work correctly. So we look at 512, 513. We go to get those memory values, which are 126 and 219. And then, yeah, so that's 512, 513 is definitely bigger than 256. And it returns the right value. Then the next time that we come back and do exactly the same thing, LSB 767 A9. Yeah, which is definitely wrong. Unless this memory location is meant to have been updated and it hasn't been. I suppose there's potential for that. Step down, step in, step in. The other thing is whether this is correct. Which equals 767. Yeah, which is 0x200, I presume. Oops, 0x2ff. Seven, 6, 7. So yeah, we look it up. We grab that. We grab +1. We look at whatever's in those things. And they turn out to be 0. RAM.memory 0x2ff 0x2ff +1 plus 2 is 0 and 169, and we would expect it to be 0 and 3. Okay, so everything looks like it's working correctly. So one of my values that I store is 0x2xf and 0x300, right? Because above it, up here, they're doing store A's, right? So store A in 300. Did these happen in my code? Yeah. Store A in 102, 200. Store A in 2ff is 0, yep. And then store A in 300 is 0, 1. So wouldn't we have expected store A in 300? And if A equals, I don't know what the 0, 1 means. A equals A9. Yeah, we load in A9, and then we store it in 300 equals 0, 1. What does equals mean? 2ff, we load 0. Load 1. Is that what it used to equal or something? So if we look at 3, yeah, then 302 should be 60 in hex, which is 96, which seems around right. So we've literally just stored these A values in there. And then we jump at 2FF, which is definitely 0, and 300. What do I do, like -1 or something? No. And then 300, which is definitely 169. I have no idea where that 03 comes from, apart from the fact that it's the address of the most significant byte. But that that ain't right. Unless, I suppose, we are meant to jump to this break, and then the break doesn't get interrupt. Push PC plus 2, push that. Increments the program counter by 1. Therefore, an RTR will go to the address of break plus 2. Yeah. Jumps transfers program execution to the following address, or to the location contained in the following address. Note there is no carry associated with an indirect jump. So an indirect jump must never use a vector beginning on the last byte of the page. For instance, the address contains 40, 3FS contains 80, 3100 contains 50. The result of jump from 3FF will transfer control to 480, as 580 took the low byte of the address from 30FF, and the high byte... Wait, what? An indirect jump must never use the vector beginning on the last byte of a page. If the address 3000 contains 40, so instead of jumping from 310, it'll go to 4080 instead of 5080. It took the low byte of the address from where you expected it to, and the high byte of the address, holy shit, this is it, from 3000. So why the fuck would it take it from 3000 instead of 3101? An indirect jump must never use a vector beginning on the last byte of a page. What's a page? Okay. Right, so it will wrap around locally, but only 30FF, only the second value will wrap around. Oh my god. Is that what it is? This one we don't care. This one can just be an mp.uint16. This one's uint16. And then MSB location. So let's see if we get up to a breakpoint. Does that work? Nice. And then when we go in LSB location, 512. Right, okay, so we want to go to our next one. Oops. Go in, step to the next line expected, step into 512 and 1. No, we don't want it to be uint 8, we just want it to wrap around if it's on the last page. Okay, so we don't want this to be a 16, but then wrap around on page boundaries. So instead of 30FF going to 3010. We actually wanted to go to 3000. So if it ends in FF, we want the bottom byte to flip back to 00. Okay, so how do we tell that? So what's LSB location? Hex of LSB location. So this is fine. So LSB location mod FF 0xFF. No, it's not right. What if it was 0x1FF? Yeah, so what if 0x300 mod by 0x100? Okay. So if MSB location modded by 100 0x100 equals 0, then MSB location equals LSB location minus 0xFF. Whatever, let's just make sure that this is correct. So we shouldn't get this on the first one. Oh, yeah, okay. Yep, so we shouldn't get this one here. Jump in after an STI absolute. But we should get it here after we get the jump in. Now MSB location is 767. So 0x2FF, 0x200, 512. What if we did CPU dot get memory at 0x200? Does it equal 3? Oh my god, it does. Holy shit. That's so rude. 512, okay. Cool. Cool. Jump in. Cool, cool, cool. Figured that bug out. Alright, so randomly page boundaries don't do it. But the NES test ROM does, just to fuck with you. Alright, that was crazy. Let's get rid of that breakpoint. Let's get rid of that breakpoint. Hey, it all works. Instruction not found. Holy fuck. Alright, what's the instruction not found? 169. Hex of 169. A9. A9, oh my god. It all ties together. Yeah, okay. Okay. What have we done here? We've jumped. What's our self.pc? $768. Which is probably not what we want. We probably want, I don't know, 0x300. And the thing at 0x300 should be A9AA, which is a load A. How do I not have load A? Did I seriously just never put in load A? Which load A? Load A immediate. It seems like something I would do. A9. Okay. Let's identify a byte. Hold up. What's identifier byte is a uint 8. Why the fuck is it a uint 8? Self-duplicate memory remote. What's PC register? Is the RAM. Wait, what? We're trying to get something, an instruction from the RAM? Oh my god. Alright. You got me. So the reason being is that this identifier byte actually comes back as a uint 8, and we just need to make sure that it actually gets cast to a bytes dot something like that. Okay. Right, so instead of having this being an actual thing, let's have this be an int. Hold up, what is... identifier byte is a bytes. So can we do identifier bytes dot hex or something? We can do dot hex, but can we do dot int? Can we do int of identifier byte? There's an int dot from bytes, but what if we did identifier bytes dot hex? Yeah, okay. Let's do that. Oh, okay. So sometimes, alright. Instance of, type of. So basically I'm no longer getting back a byte, so I'm getting back an int, and I just want to be able to cast everything that I get into an int would probably be for the best. So, screw it. If identifier byte, how do I do it, is instance of. Boom, boom, boom. if it's bytes. If it's not bytes, identify bytes. Equals, fuck that. I just want to cast it to a bytes. So bytes from identify byte. Bytes cannot be interpreted as an integer. If type bytes. Okay, finally. Nice. Data bytes match. So why don't I know my data bytes match? Because I'm getting A9, which is load A immediate, which should have one thing on it. So is there a reason that that's... so let's wait until this happens. Let's see what my identifier byte is. Identifier bytes is bytes A9. Instruction is an LDA immediate. Data bytes is self.rom.get. Yeah, okay. So this would just be self.get memory. Is the ROM one of the memory owners? Probably. So we don't actually always pull from the ROM, we can also pull from RAM, which is crazy. Alright, add, wait, what? Self.data bytes and identifier bytes. D-type, D-type, D-type. So the reality is here that this in hex form, who knows? So does it crash when I'm here? What if we do this? Yeah, it's throwing the error, right? Okay, so let's go here. So what's identifier bytes? And what's the other one? Bytes. Self.data bytes. Okay, self.get memory. So what the hell did this equal? If this equals a single int, where's my ROM? What did ROM return? It returned a bytes. So self.get memory, yada yada yada, and then okay. If the type of self.data bytes is not bytes, then self.data bytes equals bytes. Self.data bytes. We'll see if this works out when we have multiple data bytes. I think that will be useful. So self.data bytes is now AA. Yep, that seems right to me. Unknown number size. Wait, where? The hell is this going on? Data bytes equals get memory. Location, number of bytes. Oh god. So what is self.instruction length, data length? 1. What the fuck? Alright, what is self.instruction? RTS implicit, and if it's not bytes and this is passed in a 0, right, so CPU dot get memory instruction dot data length. Yeah, okay, actually, you know what, I'm going to take this back and I'm going to make this ROM still. Get the data bytes, but I'm going to do this is ROM instruction equals true, ROM instruction equals false, and let's just do a if ROM instruction, let's do this, else equals bytes. And let's just do self dot get memory. So if that is greater than 0, else self.databytes equals bytes, and empty bytes. Cool. Let's try that. Yep. Cool. Alright, so we're back to instructions not being found. Identify byte.hex. What does that equal? 04. Alright. Ah, shit. Secret instructions. Does that mean I've done everything? ADC I've done, AND I've done, ASL done, BC, BQ, bit, branches I think I've done, break I've done, BBC, BBS, DLSS, BCLV, compare, decrement, EOR, LSR, NOP, ORA, PLP. I think I may have done all the valid instructions. Am I crazy? How many are there? Wikipedia 6502. Yeah, but how many are there? Don't make me count them. 6502, number of instructions. Don't make me do it. I will do it. Kill me. Doesn't tell me. If I put this in Sublime, oops, find. That just replace it with the date. Okay, how many question marks are there? 105 matches. So if I do 256 minus 105, $151. Because I definitely couldn't do that in my head. Another stream, another day. Exactly. Welcome back, Black Stealth. I think I've implemented all the legal instructions. 151. I have. Sick. I think that's the dream. I think I'm going to finish there today. I always seem to be finishing as you arrive, Black Stealth, but yeah, that's sick. That's all the valid instructions for this thing. Now it's just invalid instructions, of which who knows how many there are. Well, probably 105 is the answer. Bugs of the day. Indirect addressing wrapping around on page boundaries. That's a ripper. God, there was another. Oh, that's right. And then wrapping around, writing multiple bytes at once, not being detected by me. So I didn't realize when I was writing 2 bytes at once, it would write the upper byte as well as the lower byte. So I was only checking for the lower byte, and so that's how it got written without me noticing. Git having a struggle. All legal instructions implemented. Sick. That is good. So what are the illegal instructions? unofficial opcodes, that's probably what they're called. Unofficial opcodes. Oh man. What? So what's an illegal opcode? 04. I have no idea. Use of unofficial opcodes is rare. Screw that. Calling it done with the CPU. What happens if I run the Mario CPU now? Instruction not found. 7F. Yeah, okay. Yeah, indeed. Alright, so 7F. Okay, so it looks like I will have to implement them. Shit. Alright. 7F. How do I even do this? 6 plus... Why the hell would you do that? I have no idea why. Anyway, what was I looking for? 7F. RRA. AX. Okay. Yeah, so... let's see. Yeah, this doesn't really tell me much beyond the... It's a bit of a nicer table. RRA. Whatever the hell RRA stands for. Nope. Nope. Doesn't tell me what it is. Legal opcodes. RRA. Oh. Is an ROR and an ADC. Okay, so this will give me a definition. Enter this password. I am human. Alright. Deal. For readability. Sweet. So this thing will give me a pretty good... ROL is the value in memory, and then ADCs it with the accumulator. Carry is set by RO operation before ADC. Nice. So this looks like it's useful. Yep. Aha. And this also looks like it's useful. Alright, so these things mostly exist. Cool. Alright, I'm going to finish up there then. Thanks for coming and watching. And yeah, finish the opcodes. It's pretty cool. Not something I was expecting to do, so that's pretty sick. I might just push up some tags. Episode 8. No problem, like cells. I've been doing this one for probably just coming up on 4 hours, so there'll be a recording of it available sometime, but a lot of pain today, a lot of fussing around with bugs. To be honest, you probably didn't miss anything too interesting. Just trying to not go insane, basically. And let's push all of these with tags. Thank you for coming and watching, Sigma981. I appreciate it. Text edit, you can die. Sublime, you're gone. You're gone. Perfect. Yeah, thanks for watching, guys, and I'll see you all when I stream next, probably next week or on the weekend or something like that. Not for a couple of days at least. But yeah, thanks for coming along, and yeah.